So last week we talked about predation. Are there any questions about the material that we did, about the understanding of prey-predator systems? Okay, so remember that you don't need to hand in your homework assignment today, and it's due on Tuesday. Okay? Huh? Tuesday. And then there'll be another one the following Tuesday. And then Thanksgiving, and then it'll be your last assignment. So we're closing in on the end of the semester with all the most exciting stuff to come. Okay, so we're going to talk now about competition. And competition can arise in a number of different ways. Can you think of different ways in which competition can arise? Is that to do with our class? Oh, okay, that's cool. Does it work? Okay, so the different ways that competition can arise. If I said there's direct competition versus indirect competition, can you think of what I might mean by that? Okay, so yeah, so indirect competition would mean I do something now that doesn't impact you immediately, but could impact you later because I ate something now that's not available for you later to eat. That's kind of indirect competition. Direct competition would be we both want to eat the same thing, and I arm wrestle you for it. Or I guess that's a polite way of saying we have a stand-up fight about it, or I push you, or I race, or I run faster and get there before you and collect it before you do. So there are two kinds of competition, direct and indirect. There's competition for resources, and there are lots of different kinds of resources. There are food resources, but then there's also, we shouldn't forget, resources, just space to exist and live. So here you see mussels, barnacles, limpets, and seaweed compete for space in an intertidal pool in a creek in Washington, or an intertidal creek. So even space is very important, and I guess we as humans are competing somewhat for space. Although, do you think we've kind of reached the density that the Earth can support for humans, space-wise? Why not? Okay, but if we wanted to, would you go there? Would you go to Alaska? Okay. Yeah, but they're growing corn. Do we need that corn? I mean, what's going to happen? We need space to, not only to sit and presently be there, but we need space to do things. So if you go down to Los Angeles, you see all these huge warehouses where stuff happens. Amazon keeps all the stuff there that they're going to send to you in the next week. Or places where manufacturing going on. Or places where food is produced. So if we take all that into account, what do you think? Do you think we can live? How many of you think we could have 100 billion people on the Earth and manage? 10 billion? 20? 30? Nobody thinks 30. So nobody has faith in technology. So it seems like one of the things that's limiting is energy. Because if we can muster energy, we can do lots of stuff. We can take all the sand and we can build things and we can go vertically to any space. We can have big machines that circulate Earth. We can make fresh water from the sea. There's huge amounts of water. So I think in the end it's all about how do we utilize energy effectively and what happens to the byproducts like heat and other things that cause changes to our atmosphere. How many of you saw on the news Obama's visit to Beijing? And so they actually shut down production for a few days for this big summit so that they could see blue sky, which they did. Anybody watch Jon Stewart here? Yeah, so they had a great thing on in Beijing. You know, don't worry about it. If it goes back to how it was, we're used to it. Anyway, I'm sure we can. If you think about it, also, do you know what proportion of food in the U.S. is totally wasted? Huh? 30. I think it's more than that, but I'm not sure the exact. Some people say at least half. But I mean, you go to restaurants and you see stuff thrown out, but maybe they're feeding it to pigs and then we eat the pigs. So there are different ways of doing things, but we also have to be careful when you recycle stuff that helps to promote disease, as we'll talk about later. But anyway, today we're talking about competition and Lotka-Volterra models. I've taken out this reference to Rockwood because we've got enough stuff to read. I've got some other articles there that we'll come to later about competition, and you might want to look at them. There's this paper by Ayala and a paper by Gilpin and Justice going back to the late 60s when mathematical ecologists were thinking a lot about how to model competition. And so we're going to trace to some extent their thoughts. And actually this work goes back to the 1930s with a scientist by the name of Gauss, who did a lot of seminal work. So what I'm going to do is we're going to talk about how you might model competition that extends the ideas that we've had on logistic growth. Okay, so if you remember, we started out, we said we have two populations, and if each of them is growing exponentially, we would just write it like that. And I just want to see what I used for the different names of the parameters. So this is where we start. Now, if the population X is not going to be able to grow without bound and is going to have intra-specific competition, it's going to compete with its own kind, then we say one way to model this is to have a carrying capacity. I'm going to call this carrying capacity S. And so this looks like the logistic equation for species 1. And then we can write down the same for species 2. So I've got 4 parameters, 2 for each species. So you've seen that. And this represents intra-specific competition of X and Y. Now, if X and Y happen to be ecological competitors, or any kind of competitor, so that they don't grow, so they grow logistically, but the competition not only comes from competing with individuals of the same kind or the same species, but competing with individuals of the other kind or the other species, then you can say, we can put in a Y over here, and an X in over here, we can add it, and we could do something like that, but then we'll say, if we do something like that and the units of X and Y are the same, that the way X competes with Y, or Y competes with X, is exactly the same as the way it competes with itself. But that's never the case, because if you look at two different kinds of individuals that are competing, very often they're similar, but they're not exactly the same. So, for example, two species of birds that compete. And the famous example are Darwin's finches on Galapagos Island, but there are many, many other examples. But if you have a look at sometimes what's called a guild of competitors, and these might be birds with different beak sizes, and there's a spectrum of resources. So the guild might be individuals who compete to eat seeds, and the resources might be seeds. Now, among the guild of competitors, the individuals with different sized beaks, and among the seeds of different sizes. And so small birds are more effective at eating small seeds and making a living off small seeds, and big birds off big seeds. But there's bound to be some overlap. So big birds can actually harvest some of the smaller seeds, but less efficiently. And small birds may be able to harvest some of the bigger seeds, but also less efficiently. Yeah. Guild, yeah. So a guild can refer in terms of human society to a group of people who do the same sort of thing, like a guild of cobblers or a guild of blacksmiths. Some of them may specialize, like some may make horseshoes, and some may make wagon axles. And they've got customers, and there's a demand for each. And if somebody tries to make everything, they're not going to be able to compete with those who specialize, because those who specialize will be more efficient and will be more effective at making what they make. So it's the same idea. And so there's a set of resources, a spectrum of resources that are going to be exploited. So these individuals in the guild make their living off the resources. As I say, it could be individuals, and there's people who have a demand out there for certain items, and then they ask people to make it. So it doesn't have to just be in biology, it can be in economics. But we can focus on biology examples. But if you say X and Y specialize in a different part of the resource spectrum, then they don't compete as intensively with one another, across the species than within the species. So you can modify this by putting an alpha over here and a beta over there. Now the alpha and the beta, you might suspect, are likely to be less than 1, which would mean that competition is less intense with the other kind than it was with your own kind. However, you can imagine situations where competition may be more intense with the other kind because you're less tolerant of those individuals and you're more likely to enter into some kind of conflict rather than sharing. So if you do it this way, all you're saying is that the way you compete with individuals from your own species is different from individuals from the other species. And if alpha is greater than 1, it's going to be more intense with the other species, and if alpha is less than 1, it's going to be more intense with your own. And the same with beta. And there could be asymmetries in alpha and beta, that alpha could be greater than 1 and beta less than 1, or they could both be greater than 1 or both less than 1. So it allows you the flexibility to study in this context. Now again, when you build models like this, they're idealizations of nature, and you might say these are canonical models. If we analyze them, we get some insights and understanding to processes of competition. Then we say, how do they apply in the real world? And when we go to the real world, we then say, what are the basic assumptions of the model, and how well might these hold up? So if you have a look at these assumptions, firstly we have the basic assumption of logistic growth for each species in the absence of the other. And then we have the assumption about competition affecting, kind of partitioning out the carrying capacity in such a way that intra and interspecific competition are going to be weighted relative to one another by the parameters alpha and beta. So alpha is how much competition does one unit of y represent to x, and beta is how much does one unit of competition of x represent to y, where it's relative to 1 when you're competing with your own kind. And then that 1 is then modulated by the size of the carrying capacity. Okay, any questions about this model? Is this about the simplest way you can think of extending the equation? So if you say, how do we model competition, what is the simplest possible way to move forward in a logical manner, is to start with what we knew about competition and how we dealt with that in the context of a single species, and just extend it in this using these very simple ideas. And again, ecologists ask, well, are there any real populations out there that seem to behave as will be predicted by the behavior of this model? So in order to know that, we first have to know how this model behaves and understand it, and what it tells us about competition. And then, once we've done that, we can go out and say, well, are there any real populations that seem to follow the predictions of the model? And if they do, then we say, well, this model seems to capture the essence of what's going on. And then as we explore further, we might say, well, this model just fails in this way or that way because there are things going on that the model doesn't account for, or that the model really seems to hold up quite well. And a lot of ecologists throughout the 70s and 80s tried to study systems, competitive systems, in the context of seeing how these models might hold up in real systems. So let's return to the projection and see how to analyze this. So how are we going to analyze the model? Is that an interesting message on your phone? You can always reply later, but I'm not going to give my lecture again. But that's your choice, I guess. What's more interesting at this moment? Now I can see this might be rather boring, but I'm trying to make it as interesting as I can. So I put in some nice pictures, like that one. And now I'm going to try and engage you by asking you what you would do to analyze this model. How would you go about? Oh. So there's our model. If I say to you, tell me what this model does, what are you going to do? Build it. Build it in Nova. Okay, let's say you built it in Nova. What value would you choose for A? What would you choose for alpha? How would it help to build it? So the problem with Nova is if you build it, if you want to know anything, you have to give these specific values. So then you can say, okay, well, let me try and... I know something about populations. I know something about how they grow. Maybe I've got two populations that grow in isolation. So if they grow in isolation, then maybe I can estimate their growth rates and carrying capacities. And so I can get some numbers in here for two real populations. But then I can say, okay, what happens if I can have a conjecture. Maybe I'll make these each a half, see what happens. So that's one way of doing it. But I've given you tools where we don't have to do that, and we're not going to go to NOVA. We're going to understand the qualitative behavior of the system without simulation. So what are we going to do? What did we do for the prey-predator equations? What did we do? Yeah, we did a phase plane analysis. So we did the phase plots, exactly. So how did we do that? Yeah, so we said, okay, let's find the null clines. So the null clines, the xdt and ydt equals 0, they're the null cline equations. So if you go through, and we will do this, you'll see that it's possible to say, okay, if I draw the null cline equations, I can see that I get what I call a trivial equilibrium. That is, x equal to 0 and y equal to 0 both make both equations simultaneously 0. Now if I choose y equal to 0, so that this term is 0, and that alpha y is 0, and I make x equals s. So that means x equal to s, y equal to 0 is also an equilibrium. So I can easily show that. Or y equals 0 and x equals k is equal to an equilibrium. These are called the isolation equilibria, because each species, in the isolation of the other, grows logistically to its carrying capacity. That's the second one. Now what I can do is I can take the first two equations up there, y equals this one. That's an equal sign. It just doesn't show up well on this projector. Let's see if I make that a 3. There. Okay. If I take this non-trivial null cline and this one, and I'm going to draw them in a minute, what you can show is that they're going to, that you can solve them simultaneously because they're just straight lines, and you can get what I'll call a coexistence equilibrium. Now the coexistence equilibrium makes biological sense only if this is positive. So it's only going to be positive if either alpha k is greater than s and alpha beta is greater than 1. So this can only be positive if the sign at the top and the bottom are the same, which means that alpha k is going to be greater than s and alpha beta is going to be greater than 1. Or if alpha k is less than s and alpha beta is less than 1, then I will get x hat equal to being positive. And the same for y hat. So these will only, so you'll only get this positive coexistence in special cases, and this coexistence is not necessarily stable. So we're going to explore when they occur and when they're going to be stable. So let's go back to, so here's a particular case. So as I said, you can take particular cases, and we're only interested in x and y in the positive domain, that's the positive quadrant. And we could look at the case alpha equal to 0.5, beta equal to 0.6. That means alpha times beta is less than 1. We could have alpha is equal to 1.2, beta is equal to 0.8. In that case, one of them is bigger than 1, one of them is smaller than 1. It so happens that their product is still less than 1. And here, they're both greater than 1. And we can use phase plane methods to analyze these cases. So you can go through this analysis yourself. I'm just going to look at the cases as they arise. So in the first case, you'll see that when I draw those two isoclines, they intersect at 0.71 and 0.57. And if I draw the arrows in there, and so I'll make this a little bigger so that we can see it better. What we see is that if you're in this part of the plane, both x and y are going to be growing, so we're going to head in this direction. If you're in D, so there's A, B, C, and D parts of the plane that have got different behavior in terms of which one is increasing, which one is decreasing. So you can go through the arguments, and you can see that in B, both are increasing. Now, we expect both to increase because if they're growing exponentially at low density before the carrying capacity kicks in, they should both be increasing. So that makes sense. If they both at very high densities, they're both above their carrying capacities, and they're starting to come down. And over here, x is growing and y is declining, and over here, x is declining and y is growing. And so if you draw the arrows, you'll see that there's actually an equilibrium here that we haven't shown, but you'll head towards this equilibrium, and so it looks like that's what we call a stable node. It attracts solutions in. Now, in the second case, so that's the first case, which we've drawn there. Now, in the second case, they don't intersect because you can show that those conditions to get x hat and y hat both positive do not hold for this set of parameters. So if we go back to that condition over here, and we said, if we put in these values for sk, alpha, and beta that I gave you, what you'll find out that one of these will be negative. And so it doesn't